Hello AP Calculus, this is Related Rates video number 2, and in this video I'm going to show you a basic related rates problem involving the area of a circle and also a basic related rates problem involving the volume of a tank. So in your notes we are looking at page 5 where we have an area problem and a volume problem. Okay, so for the area problem, we are told that the radius of a circular oil slick expands at a rate of 2 meters per minute. And we have two questions we must answer. So first question, how fast is the area of the oil slick increasing when the radius is 25 meters? And second question, if the radius is equal to 0 at time equal to 0, how fast is the area increasing after t equal to 3 minutes? Okay, so as we discussed in class, after you've read the problem, the first thing that you want to do is sketch a diagram of the situation. Okay, so we have this circular oil slick. Yes, it just happens to be circular. So we have our circle, we have a radius for our circle, and what do we know about it? Well, we are given the information that dr dt, so the rate of change of our radius, is equal to 2 meters per minute. And we are asked, so we need to know what is the rate of change of the area with respect to time when the radius is exactly 25 meters. Okay, so at the particular moment that the radius is 25 meters, they would like to know what is the rate of change of the area. Okay, so now we need to come up with an equation that relates our variables. So the equation here, we're just dealing with area of a circle and we have the radius, so our equation is just going to be the area of a circle. So area equals pi r squared. And then after you have your equation that relates all your variables, the next thing we have to do is differentiate with respect to time. So our differentiation step, I'm going to say with respect to time. So differentiate with respect to time. So left-hand side, we just get the rate of change of area with respect to time, and that's going to equal, remember pi is a constant, so we're going to have 2 pi r times the derivative of r with respect to t. And now that we have our derivative equation, now we can go ahead and plug in and solve for what they are asking us to find. So we're looking for the rate of change of the area when the radius is 25 meters. So if we go and we plug in, we're solving for dA dt. We have 2 pi. Our radius at this particular time is 25. And our rate of change of the radius is always 2 meters per minute. Okay, and once we solve that out, we get 100 pi. And our units, this is rate of change of area, and our units were meters, so area makes that meters squared. And then we're comparing that with change in time, which was in minutes. Okay, so this means if we go to interpret our answer, at the time that the radius is 25 meters, the area is increasing at a rate of 100 pi meters squared per minute. And again, we discussed in class, we know it's increasing because our rate of change is positive. Okay, so that was for part A. Part B, if we go back up and look at part B, it says if the radius is 0 at time equal to 0, how fast is the area increasing after 3 minutes? Okay, so for part B, our given information is still the same. We are still given dr dt is equal to 2 meters per minute. And this time we need dA dt when time is equal to 3 minutes. Okay, so now that we have the givens and our needs, the equation we're using is exactly the same as the previous part. So our derivative equation was dA dt was equal to 2 pi r times dr dt. All right, so we're solving for dA dt when time is equal to 3 minutes. All right, so if we look at what we need and what we have, we're solving for dA dt. We know dr dt, but we've got an issue here. Okay, we do not know what r is. But because we know the time is equal to 3 minutes, we're going to be able to solve for r. Okay, so we will do that next. We're going to have to do this off to the side. So we have to find r when time is equal to 3 minutes. All right, well, they told us that the initial condition that r at 0 was equal to 0. And we also know that dr dt is equal to 2 meters per minute. So that means that r at 3 is going to equal the initial amount at 0 plus it's going to increase 2 meters for every minute, and we're increasing for 3 minutes. So that gives us that our radius is going to be 6 meters. All right, so now we have everything that we need. We can go ahead and substitute in. So when we do that, we get dA dt is equal to 2 pi, r is 6, and dr dt was 2. So now our dA dt is 24 pi, and our units are meters squared per minute. And our interpretation is when time equals 0, or I'm sorry, when time equals 3 minutes, the area is increasing at a rate of 24 pi meters squared per minute. Okay, so the next problem we want to look at is the one right below that in your notes. We're looking at the volume of a tank. So the problem says that water pours into a fish tank at a rate of 3 feet per minute. Oh, and that, let's see, water pouring, that's a volume, so that should actually be 3 feet cubed per minute. So we're dealing with a volume. How fast is the water level rising if the base of the tank is a rectangle with dimensions of 2 by 3? Okay, so first thing we want to do is go ahead and sketch out a diagram. All right, so here is our rectangular prism. This is our fish tank, and they tell us that the dimensions of the bottom are 2 feet by 3 feet. And we do not know what the height of our tank is. But then they are pouring water into our tank. So there's the water. And let's see, what was that rate? That water was entering the tank, so that is a rate of change of volume. dB dt was entering at 3 feet cubed per minute. And the question is asking us, how fast is the water level rising if the base is a rectangle of 2 by 3? Okay, so the question is, we're looking at the rate of change of the height of the water. All right, so let's go ahead and list out the given and the needed. So the given information is that dV/dt, the rate of change of the volume of the water entering the tank, is 3 feet cubed per minute. And we need the rate of change of the height with respect to time. And they didn't really give us any particular information other than the base of our tank is going to be 2 by 3. Okay, but the base of our tank, that's not going to be changing. So those derivatives, those are going to be equal to 0. So this is a constant. And this is a constant. All right, so the equation that's going to relate all of these together, we're really just dealing with volume. So we need to know the volume formula for a rectangular prism. Well, for all prisms, so the volume for any prism is equal to the area of the base times the height. So big B is the area of the base. Okay, so depending on what type of volume you're trying to set up, that's how I remember my volume formula for any prism is just the area of the base times the height. Okay, well the area of our base is just a rectangle, so it's going to be 2 by 3, and our base in this case is constant. It is fixed. So maybe you want to write this down because we haven't talked about this in class yet. Okay, if you don't, that's fine too, and maybe it'd be easier for you to not, because then when you go to take the derivative, you're just going to end up multiplying by 0. So then, similar to the ladder problem we did in class today, the ladder wasn't changing, so we multiplied by 0. We could have just plugged that 16 in right at the very beginning. Okay, so since the area of our base is constant, that area is 6 squared feet, we're going to be able to just plug that directly in, okay, which will make our problem a little bit more simplified. Okay, so now we have our new equation. We have volume equals 6 times the height, which means when we differentiate with respect to time, we're going to get dV/dt is equal to 6 times the derivative of h with respect to time. Okay, so now if we look, we know what dV/dt is, so we can go ahead and plug that in. That was 3, and we are solving for dH/dt. So solving for dH/dt, we get 1/2, and we're looking at rate of change of height, so our units will be feet over our units of time, which were minutes. Okay, so then our interpretation is the rate of change of the heights of the water is 1/2 feet per minute. Okay, so again, those were just two basic circle, basic rectangular prism. In the next video, we're going to be looking at filling up a tank that is in the shape of a cone, and we'll also be looking at the balloon problem. So we'll see you next video.